What if I told you that everything we see, the stars, the galaxies, even the air we breathe, makes up less than 5% of the universe? The rest is a cosmic mystery, a vast invisible force we call dark energy. It's the phantom pushing our universe apart faster and faster, defying gravity's pull. And yet, despite its overwhelming presence, we have no idea what it actually is. But what if the answer has been hiding in plain sight all along? Scientists now believe that 38 undiscovered fundamental particles could be the missing pieces to this billion-year-old puzzle. Think about that for a second. Hidden within the fabric of reality, these particles might hold the key to understanding why the cosmos behaves the way it does, and perhaps even reveal forces beyond our wildest imagination. This isn't just about filling gaps in a textbook. It's about rewriting the rules of physics itself. The Standard Model, our best blueprint for how particles and forces interact, is stunningly accurate, but it's incomplete. It doesn't account for dark energy. It doesn't explain why the universe's expansion is accelerating, and that's where these 38 particles come in. Some could be messengers of entirely new forces, while others might interact with dark energy in ways we've never dreamed of. The implications are staggering. If even one of these particles exists, it could upend our understanding of reality, opening doors to technologies and discoveries we can't yet fathom. So how do we find something we've never seen? That's the thrilling part. Laboratories around the world are hunting for these elusive particles using some of the most advanced machines ever built. From underground detectors shielded from cosmic noise to particle colliders smashing matter at unimaginable speeds, the search is on. And with every experiment, we get closer to answers that could change everything. By the end of this journey, you'll see the universe not as a static backdrop, but as a dynamic, ever-evolving puzzle, one we're only just beginning to solve. So buckle up, we're about to dive deep into the unknown, where the next great discovery could be just around the corner. Dark energy isn't just some abstract idea, it's the dominant force shaping the fate of our universe. Picture this: every second, the space between galaxies stretches wider, not because of gravity pulling them together, but because of this invisible push acting on the cosmos itself. And here's the twist: the more the universe expands, the more dark energy there seems to be. It's as if empty space has its own hidden energy, growing stronger as the cosmos grows larger. Now let's talk about why this is so puzzling. For decades, scientists thought gravity would eventually slow down the universe's expansion. But in the late 1990s, observations of distant supernova revealed something shocking: the expansion wasn't slowing at all. It was speeding up. That discovery turned physics on its head. Suddenly, we had to confront the possibility that 70% of the universe's energy budget comes from something we can't see, detect, or even fully describe with our current laws of physics. So where do those 38 hypothetical particles fit in? Think of them as potential messengers from the hidden layers of reality. Some might carry forces we've never encountered, forces that don't just nudge matter but shape the very fabric of space-time. Others could interact with dark energy in subtle ways, like invisible threads weaving through the cosmos, influencing how it stretches and grows. If even one of these particles exists, it could bridge the gap between what we observe and what the Standard Model predicts. But here's the real kicker: dark energy doesn't behave like anything we've seen before. It's not a particle in the traditional sense, not a wave, not even a field we can map easily. That's why these 38 candidates are so exciting. They might represent an entirely new class of phenomena, operating under rules we haven't written yet. And if we find them, we're not just solving a cosmic mystery, we're rewriting the story of the universe itself. The Standard Model is like a brilliant but unfinished masterpiece. It explains so much, yet leaves gaping holes in our picture of reality. Imagine building a puzzle where every piece fits perfectly, only to realize you're missing entire sections of the image. That's where we are with particle physics today. The model describes 17 fundamental particles that make up everything we know, from the electrons buzzing around atoms to the quarks inside protons. It predicts their behavior with breathtaking precision, even anticipating the existence of particles like the Higgs boson before we detected it. But for all its success, it has no explanation for dark energy. It can't account for gravity's role in the quantum realm, and that's like having a map of the world that leaves off entire continents. Now, consider this. The Standard Model treats space as a static stage where particles interact, but dark energy suggests the stage itself is alive, stretching and growing. That disconnect hints at something profound. Either our model is incomplete, or we're missing a whole new layer of physics. That's where those 38 potential particles come in. Some, like axions, were originally proposed to solve unrelated quirks in quantum theory, but could unexpectedly hold clues to dark energy. Others, like sterile neutrinos, might be ghostly particles that barely interact with normal matter, yet influence the cosmos on a colossal scale. What makes this search so urgent is that these particles aren't just theoretical curiosities. They could be the missing links between the quantum world and the large-scale structure of the universe. Picture a bridge connecting two islands. On one side, the subatomic realm with its precise rules. On the other, the vast, mysterious expanse of dark energy. Without that bridge, we're stuck staring at one island, wondering how it relates to the other. And here's the fascinating part. These particles might not be hiding in some distant corner of space. They could be all around us, slipping through our detectors unnoticed because they interact so weakly with ordinary matter. It's like trying to catch fog with a net. That's why experiments are getting more creative, using ultra-sensitive lab setups, repurposing ancient minerals as particle traps, even monitoring the afterglow of the Big Bang for faint whispers of these elusive entities. The hunt isn't just about filling gaps in a theory. It's about discovering whether our universe operates by rules we haven't even imagined yet. Particle accelerators like the Large Hadron Collider have revolutionized our understanding of the universe, smashing particles together at nearly the speed of light to uncover secrets like the Higgs boson. But what if the next cosmic revelations can't be found in a collider? Those 38 elusive particles might play by entirely different rules, so massive they're beyond our current energy thresholds, so weakly interacting they slip through detectors like ghosts, or even existing in dimensions we can't yet perceive. Imagine trying to catch a shadow with bare hands. That's the scale of the challenge physicists face. Take the hypothetical sterile neutrino, for example. Unlike its known cousins, this particle might interact only through gravity, making it nearly invisible to traditional experiments. Or consider axions, particles so light and fleeting they could pass through a planet as if it weren't there. These aren't just fringe ideas, they're serious candidates that could explain why dark energy's influence grows as the universe expands. The problem: our tools were built to find particles that behave predictably. Dark energy's messengers might not follow those rules at all. That's why scientists are turning to ingenious alternatives. Deep underground, ultra-sensitive detectors wait for the faintest tremors of a passing particle. In space, telescopes scan for anomalies in the cosmic microwave background, echoes of the Big Bang that might hide clues. Some researchers even propose repurposing Earth's magnetic field as a giant particle trap. The stakes couldn't be higher. If these particles exist, they're not just minor additions to the standard model. They're keys to unlocking why 70% of the universe behaves in ways that defy all expectations. And then there's the wild card, extra dimensions. String theory suggests our universe might have hidden layers, curled up so tightly we've never noticed. Particles drifting through these dimensions could explain dark energy's pervasive yet invisible nature. Picture ants crawling on a sheet of paper, unaware of the third dimension above them. Are we missing a similar cosmic perspective? The hunt is as much about creativity as it is about brute force. From repurposing ancient gold mines as particle observatories to studying the subtle wobbles of distant neutron stars, every unconventional approach brings us closer to answers. The next breakthrough might not come from a louder collision, but from a whisper in the dark, a signal so quiet we've been missing it all along. One thing's certain, the universe still holds mysteries that challenge not just our tools, but our very imagination. Among the 38 hypothetical particles that could unlock dark energy's secrets, one stands out as particularly elegant: the quintessence particle. Unlike the cosmological constant, which imagines dark energy as a static force woven into space itself, quintessence proposes something far more dynamic. Picture a cosmic chameleon, a form of energy that evolves over time, growing stronger or weaker as the universe expands. And if quintessence is real, it would need a messenger particle, a fundamental piece of the puzzle that's been hiding in plain sight. What makes this idea so compelling is how neatly it solves two problems at once. First, it explains why dark energy's influence seems to grow as the universe stretches. Second, it could tie into cosmic inflation, that explosive moment just after the Big Bang when the universe expanded faster than light. Imagine a single particle responsible for both the universe's birth and its accelerating fate, a cosmic architect shaping reality at its largest scales. But here's the catch: if the quintessence particle exists, it's likely incredibly shy. It might interact with ordinary matter so weakly that even our most sensitive detectors miss it, like trying to hear a whisper in a hurricane. Some theories suggest it could change mass depending on its environment, making it even harder to pin down. That hasn't stopped scientists from looking, though. Experiments are hunting for subtle ripples in gravitational waves or tiny shifts in the cosmic microwave background, hints that this ghostly particle might be leaving fingerprints on the universe. And then there's the tantalizing possibility that quintessence isn't just one particle, but a family. Just as quarks come in multiple flavors, quintessence might have variations we've yet to imagine, each playing a different role in the cosmos. If that's true, discovering even one could open the door to an entirely new branch of physics. Now, shift gears to another contender, the axion. Originally proposed to solve a puzzle in quantum mechanics, this lightweight particle has quietly emerged as a dark energy dark horse. Unlike quintessence, axions wouldn't change over time, but they could still hold the key to why empty space seems to push the universe apart. The beauty of the axion is its duality. It's simple enough to fit neatly into existing theories, yet strange enough to explain the unexplainable. What both these particles share is their ability to bridge the gap between the quantum world and the cosmos. They're not just missing pieces, they're potential master keys, unlocking doors we didn't even know were closed. And with every experiment, we get closer to finding out whether nature chose elegance, simplicity, or something entirely unexpected. The hunt isn't just about filling gaps in a theory. It's about rewriting the story of the universe itself. Now, let's turn to another fascinating contender in the hunt for dark energy's secrets, the chameleon particle. Unlike any particle we've discovered so far, this one has a unique trick up its sleeve. It changes its behavior depending on where it is. Picture a cosmic shape-shifter, blending into its surroundings so perfectly that it becomes nearly invisible here on Earth, where matter is dense, but revealing its true nature in the emptiness of space. That adaptability isn't just clever, it could explain why dark energy's effects are so hard to pin down. If these particles exist, they might be hiding in plain sight, masking their presence where we'd most likely look for them. What makes the Chameleon particle so compelling is how neatly it solves a major puzzle. If dark energy were constant everywhere, we'd expect to see its influence even in our own solar system. But so far, it's only detectable on the grandest scales, like the vast gaps between galaxies. Chameleon particles could be the reason. In crowded regions like near stars or planets, they might suppress their effects, staying quiet to avoid detection. But in the void of intergalactic space, where there's little matter to hide behind, they could unleash their full force, driving the universe's accelerating expansion. It's like a cosmic game of hide and seek, where the rules change depending on where you're standing. Scientists aren't just theorizing about these elusive particles, they're actively hunting for them. Ultra-sensitive experiments like torsion balance devices are searching for faint, unexpected forces that could betray the chameleon's presence. These setups are so precise they can detect pushes and pulls tinier than the weight of a single bacterium. Imagine trying to measure a whisper in a thunderstorm. That's the level of precision required. And if they succeed, it wouldn't just confirm a new particle. It would revolutionize our understanding of how the universe's hidden forces operate, revealing a dynamic interplay between matter and energy that's been invisible to us until now. But the Chameleon isn't the only player in this cosmic mystery. Supersymmetry, a bold theoretical framework, suggests that every known particle has a hidden twin, a superpartner with unique properties. If this theory holds, it could add a whole new roster of particles to our search, particles that might interact with dark energy in ways we've never considered. Some of these superpartners could be heavy, slow-moving, and incredibly rare, while others might be fleeting, zipping through space without a trace. Together, they could form a hidden network of influences, shaping the universe from behind the scenes. The beauty of supersymmetry is that it doesn't just solve one problem. It could explain dark energy, unite gravity with quantum mechanics, and even account for the mysterious dark matter that holds galaxies together. But here's the catch: despite decades of searching, we haven't found direct evidence of these superpartners yet. That hasn't deterred physicists, though. Every null result narrows the possibilities, guiding us closer to the truth. Whether it's the Chameleon, supersymmetry, or something entirely unexpected, one thing is clear: the universe still has secrets to share, and the next great discovery could be just around the corner. Supersymmetry isn't just a fringe idea. It's a sweeping vision that could redefine reality as we know it. At its core, it proposes an elegant symmetry between matter and force, where every particle we've discovered has a hidden twin. Electrons, quarks, even the Higgs boson would each have a superpartner with unique properties, like a cosmic mirror image waiting to be uncovered. If this theory holds, it wouldn't just double the number of particles overnight. It could solve some of the universe's deepest mysteries, including the enigma of dark energy. But here's the catch: despite decades of searching, we haven't found a single superpartner yet. That doesn't mean they don't exist. Some might be so massive that even our most powerful colliders can't produce them. Others could decay almost instantly, vanishing before our detectors catch a glimpse. It's like trying to photograph a firefly in a thunderstorm. The signals are fleeting, drowned out by the noise of more familiar particles. Yet the stakes are too high to give up. Supersymmetry could explain why dark energy's influence seems so finely tuned. Imagine one of these shadow particles, the gravitino, for instance, a hypothetical superpartner of the graviton. If it exists, it might interact with dark energy in ways that balance the universe's expansion, acting as a cosmic counterweight to prevent runaway acceleration. Or consider the Neutrino, a leading dark matter candidate that could also play a role in dark energy's behavior. These particles wouldn't just fill gaps in our theories, they'd weave them together into a grander tapestry. Now shift the lens to another radical possibility: extra dimensions. String theory suggests our universe might not be limited to the 3 dimensions we experience. Hidden layers curled up smaller than an atom could harbor particles that occasionally leak into our reality, influencing dark energy in ways we can't yet measure. Picture ants crawling on a sheet of paper, unaware of the world above them. What if dark energy's secrets lie in dimensions we've yet to perceive? Experiments are already probing these ideas. Particle colliders search for energy missing from collisions, a potential clue that particles are escaping into higher dimensions. Gravity waves, ripples in space-time itself, might carry traces of these hidden realms. And if we find evidence, even indirect, it would be a paradigm shift on par with discovering quantum mechanics. The universe, it seems, still has cards left to play. Whether through supersymmetry, extra dimensions, or something entirely unforeseen, the answers to dark energy's riddles may lie just beyond the edge of our current understanding. The search for these particles isn't just academic. It's a race to uncover the hidden mechanics of reality itself. Every null result, every tantalizing near miss, brings us closer to knowing whether our universe operates by rules we've yet to imagine, or if the truth is stranger still. If you think our universe is limited to the 3 dimensions we move through every day, think again. String theory paints a far stranger picture, one where space-time isn't flat and static, but rippling with hidden layers curled up so tightly they're smaller than an atom. These extra dimensions aren't just theoretical fluff, they could be the missing link to understanding dark energy. Imagine particles that don't just move left, right, or up, but into directions we can't even point to. Some of those 38 undiscovered particles might be doing exactly that, drifting through higher dimensions while their gravitational whispers bleed into our reality. This isn't science fiction. If these higher dimensional particles exist, they could explain why dark energy seems to permeate empty space without leaving a trace. Picture a sheet of paper, a 2-dimensional world where ants crawl along the surface, oblivious to the 3rd dimension above them. Now imagine one of those ants suddenly feeling a tug from an unseen force. That's what might be happening with dark energy. Particles interacting in extra dimensions could be nudging our universe apart, their influence faint but pervasive, like shadows cast from a world we can't see. The real challenge, detecting something that barely interacts with our dimension. Most particles we know, electrons, quarks, even neutrinos, leave some trace, however faint. But these higher dimensional travelers might only communicate through gravity, the weakest and most elusive of the fundamental forces. That's like trying to hear a single note in a symphony played 1,000 miles away. Current particle colliders and detectors aren't built for this. They're designed to catch particles that obey the rules of our 3-dimensional playground. But here's where things get exciting. Future experiments might finally crack this dimensional veil. Gravitational wave observatories like LIGO or the upcoming LISA mission could detect ripples in space-time caused by these hidden particles. Even subtler anomalies in the cosmic microwave background, the afterglow of the Big Bang, might carry fingerprints of extra dimensions. And then there's quantum foam, the turbulent, frothy fabric of space-time at the tiniest scales. Some theories suggest dark energy could arise from the seething energy of this quantum vacuum, where particles flicker in and out of existence faster than we can measure. So what does this mean for our 38 missing particles? They might not just be new pieces of the puzzle, they could be pieces from a puzzle we didn't even know existed. If even one of them is tied to extra dimensions or quantum foam, it would rewrite our understanding of reality's deepest layers. The hunt isn't just about filling gaps in a theory. It's about discovering whether the universe is far bigger, stranger, and more interconnected than we ever dared to dream. Now, let's zoom in even closer to the chaotic, bubbling realm of quantum foam. At scales a billion times smaller than an atom, space-time isn't smooth. It's a churning sea of virtual particles popping into existence and vanishing in an instant. This isn't just empty space, it's a frenzy of energy, and some scientists believe it could hold the key to dark energy's mysterious push. Imagine blowing up a balloon while tiny, invisible hands stretch it from the inside. That's what quantum foam might be doing to the cosmos, every fleeting particle adding a microscopic kick to the universe's expansion. The staggering part. Calculations suggest the vacuum energy from this quantum frenzy should be astronomically stronger than what we observe. This mismatch, known as the cosmological constant problem, is one of physics' greatest embarrassments. But what if those 38 particles help balance the equation? Some might act as cosmic dampeners, tempering the vacuum's wild energy into the subtle force we call dark energy. Others could be intermediaries, translating between the quantum realm and the large-scale structure of space-time. Experiments are already probing these ideas. Ultra-precise atomic clocks measure whether fundamental constants change over time, a potential clue that quantum foam's properties aren't static. Meanwhile, tabletop experiments search for minuscule fluctuations in gravity that could betray hidden dimensions or new particles. It's a race to uncover whether dark energy is a feature of space itself or the echo of something far stranger lurking beneath. One thing's certain, the answers won't come easily. But with every experiment, we're not just testing theories, we're peering into the universe's blueprint, searching for the hidden signatures of reality's architects. Whether through extra dimensions, quantum foam, or particles we've yet to name, the truth is out there, waiting to rewrite the story of everything. Deep beneath the smooth surface of reality, the universe churns with an invisible chaos quantum foam. This isn't just empty space, it's a seething ocean where particles flicker into existence and vanish in less than a heartbeat, borrowing energy from the void itself. These fleeting virtual particles shouldn't just be a curiosity, they should be flooding the cosmos with unimaginable energy, enough to rip the universe apart. Yet when we calculate their cumulative effect, the numbers are catastrophically wrong. The math predicts a dark energy force one followed by 120 zeros stronger than what we observe. It's like expecting a hurricane and feeling only a breeze, a discrepancy so vast it's been called physics' most embarrassing problem. But what if those 38 undiscovered particles hold the key to this cosmic accounting error? Imagine them as invisible regulators tempering the quantum foam's frenzy. Some might act like pressure valves, siphoning off excess energy into hidden dimensions or converting it into forms we can't yet detect. Others could rewrite the rules of quantum fields themselves, subtly altering how virtual particles behave. Picture a glass of soda fizzing wildly. Those particles might be the unseen hand that calms the foam, preventing it from overflowing. This isn't just about fixing a math problem. If these particles exist, they'd reveal a breathtaking truth. The vacuum of space isn't passive. It's a dynamic, almost alive medium with its own hidden layers of interaction. The implications ripple across physics. Suddenly, dark energy isn't just some mysterious push, it's the net effect of countless quantum corrections, a delicate balance struck by particles we've yet to meet. Yet quantum foam isn't the only path forward. Some theorists argue we've been looking at the problem backward. Instead of tweaking particles, maybe we need to rethink gravity itself. Modified gravity theories propose that Einstein's equations, while stunningly accurate, might miss subtle nuances at cosmic scales. What if gravity weakens differently over vast distances, mimicking the effects of dark energy without invoking unknown particles? It's a radical idea, but then again, so was quantum mechanics a century ago. The beauty of this moment in physics is that we're not stuck with one explanation. Whether through undiscovered particles, revamped gravity, or something even stranger, the puzzle of dark energy is forcing us to question fundamentals we once took for granted. And with each new experiment, from ultra-precise measurements of gravitational waves to lab tests probing quantum vacuum fluctuations, we're not just searching for answers. We're rewriting the very definition of what it means to explore the universe. What if the answer to dark energy's mystery isn't hidden in undiscovered particles but in gravity itself? For over a century, Einstein's theory of general relativity has been our gold standard for understanding gravity, describing it as the curvature of space-time by mass and energy. But here's the catch: when we apply those equations to the universe's accelerating expansion, they fall short. That's led some physicists to propose a radical idea. Maybe we've been missing something fundamental about gravity all along. Enter modified Newtonian dynamics, or MND. This theory suggests that gravity doesn't behave the same way at all scales. On Earth or within our solar system, Newton's and Einstein's laws hold up beautifully. But venture into the vast emptiness between galaxies, and gravity might play by different rules, weakening just enough to mimic the effects of dark energy without invoking any mysterious particles. It's like discovering that the rules of chess change slightly when you're playing on a board the size of a city. Yet MND isn't without its critics. For starters, it struggles to explain certain cosmic observations, like the behavior of galaxy clusters or the precise patterns in the cosmic microwave background. More importantly, it feels like a patch rather than a complete overhaul, a tweak to existing equations rather than a deeper revelation about how the universe works. That's where those 38 hypothetical particles could come back into play. If gravity itself is mediated by particles we haven't found yet, like the graviton, or something even stranger, they might bridge the gap between Einstein's theory and dark energy's puzzling effects. The debate between these two camps isn't just academic. It's a clash of philosophies. On one side, particle enthusiasts argue that nature loves symmetry, and filling the standard model's gaps with new particles is the most elegant path forward. On the other, gravity modifiers insist we're overcomplicating things, that the simplest explanation lies in refining what we already know. Both sides agree on one thing, though: our current understanding is incomplete. Now let's throw neutrinos into the mix. These ghostly particles, barely interacting with matter, were once thought to be massless. Then we discovered they have a tiny bit of heft, enough to reshape our models of the universe. Could they, or their hypothetical cousins like sterile neutrinos, hold clues to dark energy? Some theories suggest neutrinos might interact with hidden sectors of physics, acting as messengers between our world and whatever's driving the cosmos apart. The beauty of this moment in physics is that we don't have to choose just one path. Experiments are testing both modified gravity and new particles, racing to see which, if either, holds up under scrutiny. Whether the answer lies in rewriting gravity's rulebook, uncovering new particles, or some wild combination of the two, one thing's certain: the universe still has surprises in store. And the next big discovery could come from anywhere, even the quietest, most elusive particles we've ever chased. Neutrinos are the ultimate cosmic ghosts, particles so elusive they can pass through light years of lead without a single interaction. Billions stream through your body every second, leaving no trace. But what if their strangest cousins, sterile neutrinos, hold the secret to dark energy? Unlike ordinary neutrinos, which occasionally bump into matter via the weak force, sterile neutrinos would interact only through gravity, making them nearly invisible to our detectors. That's why they're such compelling dark energy candidates. If even a fraction of those 38 missing particles are sterile neutrinos, they could be the hidden architects of cosmic acceleration, subtly warping space-time on a universal scale. Here's where it gets even more intriguing. Ordinary neutrinos already defy expectations. They oscillate, changing flavors between electron, muon, and tau types as they travel. But certain experiments have detected anomalies in these oscillations, tiny discrepancies that sterile neutrinos could neatly explain. Picture a hidden orchestra tuning just out of earshot. Sterile neutrinos might be the unseen musicians, influencing the notes we can hear without ever stepping into the spotlight. If they exist, they wouldn't just solve the dark energy puzzle, they'd rewrite our understanding of neutrino physics itself. The challenge, detecting something that barely interacts with reality. Traditional particle detectors rely on catching flashes of light or ionized trails left by collisions, but sterile neutrinos would slip through these nets effortlessly. That's why scientists are turning to indirect methods, like monitoring the subtle imprints sterile neutrinos might leave on the cosmic microwave background or tracking the peculiar way galaxies cluster across the universe. Even the faintest gravitational tugs could betray their presence. Now, shift focus to another dark horse in this cosmic mystery, the axion. While sterile neutrinos are ghostly giants, axions are featherweight phantoms, theorized to be billions of times lighter than electrons. Originally proposed to solve a quantum quirk involving the strong nuclear force, axions have since emerged as unexpected dark energy contenders. Their magic lies in their duality. They could behave like waves rippling through space, collectively exerting a gentle push that drives cosmic expansion. What makes axions so appealing is their elegance. Unlike sterile neutrinos, which require entirely new physics, axions fit snugly into existing theories, almost as if the universe left a placeholder for them. Some models even suggest axions could condense into a cosmic fluid, permeating space with an energy density that precisely matches dark energy's observed effects. It's like discovering a hidden gear in a clockwork universe, one that's been quietly ticking all along. The hunt for axions is just as creative as the search for sterile neutrinos. Laboratories use ultra-sensitive magnetic fields to coax axions into revealing themselves, while telescopes scan distant neutron stars for anomalous light emissions that might signal their decay. If either particle or both are part of dark energy's story, the implications would stretch far beyond cosmology. They could unlock new technologies, redefine fundamental forces, and even reveal hidden layers of reality we've only begun to dream of. One thing's certain, the universe's greatest mysteries won't surrender their secrets easily. Whether through sterile neutrinos, axions, or something entirely unforeseen, the answers are out there, waiting for the next bold experiment to shine a light into the dark. Axions began their journey in physics as a clever solution to a puzzle that had nothing to do with dark energy. Scientists proposed these hypothetical particles to fix a nagging inconsistency in quantum chromodynamics, the theory governing the strong nuclear force that holds atoms together. The problem was this: according to calculations, the strong force should violate a fundamental symmetry called charge parity, or CP, yet experiments showed no trace of that violation. Axions emerged as the perfect fix, silently restoring balance to the equations without leaving a trace. But in the decades since, they've taken on a far grander role, potentially holding the key to not one but two of the universe's greatest mysteries: dark matter and dark energy. What makes axions such compelling dark energy candidates is their bizarrely low mass and wave-like behavior. These particles could be billions of times lighter than electrons, so wispy that they'd barely interact with ordinary matter. But in vast numbers, they might coalesce into a cosmic ocean, filling every corner of space with an energy field that subtly pushes the universe apart. Picture a gentle breeze you can't feel, yet over billions of years it reshapes entire galaxies. That's the scale of influence axions could wield, a whisper with the power to bend the cosmos. The hunt for axions is already underway in labs around the world. Leading the charge is the Axion Dark Matter Experiment, or ADMX, which uses powerful magnetic fields to coax these elusive particles into revealing themselves. Inside its cryogenically cooled chamber, scientists hope to catch the faintest signals of axions converting into microwave photons, a process so rare it's like listening for a single raindrop in a thunderstorm. But ADMX isn't alone. Other experiments like CAP in South Korea and Haystack in the United States are tuning into different frequency bands, scanning the cosmic static for axions of varying masses. Even the cosmos itself is a laboratory. Astronomers search for anomalous starlight that might hint at axions decaying in the magnetic fields of neutron stars. Now here's where things get truly fascinating. If axions exist, they might not just be one monolithic particle. Theoretical models suggest a whole spectrum of axion-like particles, each with slightly different properties. Some could be heavy, lurking in the shadows as dark matter. Others might be feather-light, weaving through space as dark energy. And if even one of these variants is real, it could slot neatly into that list of 38 missing particles, solving multiple cosmic riddles at once. But the story doesn't end there. Axions could also bridge two of the universe's most dramatic epochs: cosmic inflation and dark energy's reign. Inflation, that explosive moment when the universe expanded faster than light in the first fraction of a second after the Big Bang, might have been driven by a field not unlike the one axions could create. Some theorists propose that the same kind of energy fueling inflation then could have evolved into the dark energy we see today. It's a poetic symmetry. The force that birthed the cosmos might still be shaping its fate, hidden in plain sight as these ghostly particles. The implications are staggering. Discovering axions wouldn't just fill a gap in the standard model, it would reveal a hidden thread connecting the universe's birth, its structure, and its ultimate destiny. And with every experiment, we're not just hunting for a particle. We're chasing the possibility that the answers to our biggest questions have been floating through space all along, quiet and patient, waiting for us to notice. Cosmic inflation wasn't just a fleeting moment. It was the universe's most dramatic growth spurt, stretching space faster than light in the first fraction of a second after the Big Bang. But what if that explosive energy never truly vanished? Some theories propose that the field responsible for inflation didn't disappear, it simply evolved, transforming into the dark energy we see today. Picture a roaring fire dwindling to embers, still radiating heat long after the flames are gone. Those 38 undiscovered particles might be the cosmic embers, remnants of inflation's fiery birth, quietly shaping the universe's expansion billions of years later. This idea isn't just poetic, it's a potential game changer. If dark energy is inflation's faded echo, it could explain why the universe's acceleration seems so finely tuned. Inflation needed to be powerful enough to smooth the cosmos into the uniform expanse we observe, yet delicate enough to avoid tearing space-time apart. Dark energy in this scenario would be the leftover balance, a gentler but persistent push, like a pendulum slowing to a steady rhythm after its initial wild swing. And those missing particles, they might be the messengers of this transition, carrying clues about how the universe shifted from explosive birth to its current measured expansion. But here's the twist. If inflation's field decayed into dark energy, it might not have stopped everywhere. Some corners of the cosmos could still be inflating, hidden beyond our observable horizon. This eternal inflation theory suggests our universe might be one bubble in an endless froth of expanding space, each with its own physics. Those 38 particles could be the key to testing this mind-bending idea. If they bear signatures of inflation's original field, unique spins, energies, or decay patterns, they'd offer a window into realms we can't yet see. Now, shift focus to the universe's ultimate fate. Dark energy doesn't just shape the cosmos, it decides how the story ends. If it remains constant, galaxies will continue drifting apart until they're lost in isolation, their light too faint to reach one another. But if it strengthens over time, the outcome grows darker. A Big Rip scenario could tear atoms apart, unraveling reality itself. Alternatively, if dark energy weakens, gravity might regain dominance, pulling everything back in a cosmic collapse. Those 38 particles hold the answer. Their properties could reveal whether dark energy is steady, evolving, or something far stranger. Imagine discovering one that interacts with gravity in a way that dampens dark energy's effects over time, like a cosmic brake pedal. Or another that hints at sudden shifts in the vacuum of space, suggesting the universe's expansion isn't as predictable as we thought. The stakes couldn't be higher. We're not just piecing together the past, we're reading the universe's destiny in particles we've yet to meet. And with every experiment, we edge closer to knowing whether the cosmos is headed for quiet solitude, violent dissolution, or a fate we haven't even dreamed of. The fate of our universe hinges on dark energy's hidden rules, and those 38 elusive particles could be the crystal ball revealing what comes next. Picture a cosmic tug of war. On one side, gravity's relentless pull, trying to hold the universe together. On the other, dark energy's mysterious push, stretching space itself. Which force wins determines whether we're headed for eternal expansion, violent disintegration, or a dramatic collapse. The scariest scenario, the Big Rip. If dark energy grows stronger over time, it wouldn't just separate galaxies, it would shred stars, planets, and even atoms themselves, reducing reality to isolated particles drifting in an infinite void. It's a fate so extreme, it makes black holes seem gentle by comparison. But there's another possibility, the Big Crunch. Imagine dark energy losing steam, its influence fading until gravity finally takes over. Galaxies would reverse course, rushing back toward each other in a cosmic reunion that ends in a fiery collapse. The universe would rebound into a singularity, perhaps birthing a new Big Bang in an endless cycle of death and rebirth. Then there's the quietest ending, the heat death, where dark energy remains constant and the universe expands forever, growing colder and darker until every star burns out and every black hole evaporates. Here's where those 38 particles become cosmic fortune tellers. If one of them interacts with dark energy in a way that strengthens its push, the Big Rip becomes more likely. Another might act as a dampener, subtly weakening dark energy's grip over billions of years, steering us toward the crunch. Or perhaps they'll reveal that dark energy isn't constant at all, that it fluctuates in ways we can't yet predict, making the universe's fate even wilder than we've imagined. To unravel these possibilities, astronomers don't just stare at the sky, they turn the cosmos into a laboratory. By measuring the light from distant supernova, they track how fast the universe's expansion has accelerated over billions of years. Galaxy surveys map the large-scale structure of the cosmos, revealing how dark energy sculpts the distribution of matter. Even gravitational waves, the ripples from colliding black holes, carry hints about how space-time itself stretches under dark energy's influence. But the real breakthrough could come from spotting one of those 38 particles in action. If a detector catches a whiff of an axion or a sterile neutrino interacting with dark energy's field, it wouldn't just be a discovery, it'd be a glimpse into the universe's expiration date. The hunt isn't just about satisfying curiosity, it's about learning whether the cosmos is fated for solitude, chaos, or rebirth. And with every observation, we're not just reading the universe's past, we're decoding its destiny. Observing dark energy's fingerprints across the cosmos isn't as simple as pointing a telescope at the sky. Astronomers have to become cosmic detectives, piecing together clues from the universe's grandest structures and most violent explosions. One of their most powerful tools, supernova, stellar detonations so bright they outshine entire galaxies. By measuring the light from these explosions billions of light years away, scientists can track how fast the universe was expanding at different points in time. It's like finding mile markers on a highway, each one revealing how much the road has stretched since the light left it. These supernova surveys were how we first discovered dark energy's existence in the late 1990s, and they're still delivering surprises today. But supernova aren't the only witnesses to dark energy's work. Look at the way galaxies cluster across the cosmos, forming vast webs of matter separated by even vaster voids. Dark energy's push alters this cosmic architecture, subtly changing how these structures grow over time. Projects like the Dark Energy Survey map millions of galaxies to spot these distortions, creating a three-dimensional blueprint of the universe's skeleton. The James Webb Space Telescope takes this even further, peering back to the universe's infancy to see how dark energy's influence has evolved. Its infrared eyes can spot galaxies so distant, their light has been stretched into invisibility by lesser telescopes, offering a front-row seat to the universe's expansion history. Yet for all these advances, directly detecting those 38 hypothetical particles demands more than just observation. It might require reimagining how we study the cosmos altogether. Gravitational lensing, the bending of light around massive objects, could offer a backdoor. If dark energy's particles warp space-time in unique ways, they might leave faint imprints on the paths of distant starlight. Similarly, anomalies in the cosmic microwave background, the afterglow of the Big Bang, might hide whispers of these particles' interactions. Some theorists even propose hunting for faint, repeating patterns in gravitational waves, the ripples from colliding black holes, which could carry traces of dark energy's hidden mechanics. The challenge: these signals would be unimaginably subtle, buried under cosmic noise and the limits of our current technology. Detecting them would mean building instruments sensitive enough to measure distortions smaller than an atom across miles of space. It's a task that pushes engineering to its breaking point, yet the payoff could redefine physics. Imagine a future where we don't just infer dark energy's existence from its effects, but finally meet its fundamental components face to face. That's the frontier we're racing toward, where every new telescope, every upgraded detector, brings us closer to the universe's best-kept secrets. The search isn't just about solving a cosmic puzzle. It's about proving whether humanity's ingenuity can uncover truths hidden in the fabric of reality itself. And with every observation, we're not just collecting data, we're rewriting the story of how the universe works, one particle at a time. Detecting particles that barely leave a trace is like trying to catch smoke with your bare hands. Every signal is faint, every interaction fleeting. The technological leaps needed to spot these elusive particles push the boundaries of engineering and imagination. Take future colliders, for instance. While machines like the Large Hadron Collider smash protons at nearly the speed of light, the next generation projects like the proposed Future Circular Collider aim to reach energies so high they could produce particles massive enough to interact with dark energy's hidden forces. But even these behemoths might not be enough. Some of those 38 particles could be so weakly interacting that they'd slip through undetected, like shadows passing through a sieve. That's why scientists are turning to space itself as a laboratory. Imagine telescopes so precise they can measure the gravitational warp of a single atom from orbit. Missions like the Laser Interferometer Space Antenna, or LISA, plan to do just that, using lasers to detect ripples in space-time so subtle they could reveal particles interacting only through gravity. Meanwhile, quantum sensors on Earth are achieving near-miraculous sensitivity. These devices exploit the bizarre rules of quantum mechanics to spot disturbances smaller than a proton's width, potentially catching whispers of particles that bypass ordinary matter entirely. Yet the challenges go beyond pure physics. Building these tools requires global cooperation and funding on a scale rarely seen outside wartime efforts. The hunt for dark energy's particles isn't just a scientific endeavor. It's a test of humanity's willingness to invest in questions without immediate answers. Some of these particles might never be seen in the traditional sense. Instead, their existence could be inferred from the way they sculpt the cosmos, subtly bending galaxy clusters or leaving faint fingerprints in the afterglow of the Big Bang. The road ahead is undeniably long, but the stakes redefine what's possible. Discovering even one of these particles wouldn't just fill a gap in a textbook, it would rewrite our understanding of reality's deepest layers. And as competing theories vie for dominance, each with its own vision of dark energy's true nature, the race to build these detectors isn't just about technology. It's about which ideas get to shape the future of physics. Not everyone agrees that dark energy's secrets lie in undiscovered particles. Some physicists argue we're chasing phantoms, that the answer isn't in new physics, but in fixing flaws in our existing frameworks. Take quantum field theory, the backbone of particle physics. Critics point out its glaring blind spot. It predicts a vacuum energy trillions of times stronger than dark energy's observed effects. That's not just a rounding error. It's like expecting a tidal wave and getting a ripple. Could the solution be rewriting quantum theory itself, tweaking equations to account for hidden cancellations or undiscovered symmetries? Then there's the space-time revisionists. If Einstein's general relativity falters at cosmic scales, dark energy might not be a thing at all, but an illusion caused by gravity behaving differently over vast distances. Modified gravity theories like Mund galactic scale tweaks suggest we've misread the universe's expansion entirely. Imagine measuring a rubber band stretch while missing that it's also thinning. Our instruments might confuse weakening gravity for an invisible force. Proponents of the 38-particle hypothesis counter with elegance. Nature loves symmetry, they argue, and filling the standard model's gaps mirrors past breakthroughs like the Higgs boson. When skeptics ask why we haven't detected these particles yet, the response is simple. We've rebuilt detectors before to catch neutrinos and gravitational waves. Why assume our current tools are final? But beneath these debates lies a deeper question. What does it mean to solve dark energy? If we find those particles, do we truly understand them, or just push the mystery one layer deeper? Philosophy creeps into physics here. Some argue dark energy isn't a problem to be fixed, but a signpost pointing to a grander theory, one where particles, space-time, and quantum fields unite seamlessly. Others warn against overfitting nature to our models, recalling how Einstein initially dismissed cosmic expansion as his greatest blunder. The stakes transcend academia. If dark energy stems from new particles, it implies undiscovered forces permeating reality, technologies waiting in the wings. If it's revised gravity, we're redefining the cosmos's scaffolding. Either way, the answer won't just fill textbooks. It'll redefine how humanity sees its place in the universe. What does it mean to uncover the building blocks of reality itself? If dark energy's secrets lie in those 38 hypothetical particles, we're not just solving a physics puzzle, we're confronting questions that have haunted philosophers for millennia. Is the universe a finely tuned machine, its laws perfectly balanced to allow life? Or are we one cosmic accident in a vast multiverse, where different realms operate by wildly different rules? The answers could redefine our place in existence. Consider the staggering precision of dark energy's strength, strong enough to push galaxies apart, yet weak enough to avoid ripping atoms to shreds. If those particles explain this balance, it might suggest the cosmos was designed for stability, or it could point to something stranger, an infinite landscape of universes, each with its own random dark energy value, and we simply inhabit the rare one where conditions allow galaxies and thinkers to exist. This anthropic principle divides scientists. Some see it as a cop-out, others as the only logical conclusion if multiverses are real. Now layer in causality. If dark energy's particles influence space-time's expansion, do they also shape the arrow of time itself? Could their interactions set the irreversible flow from past to future? Philosophers and physicists alike grapple with whether time's direction is fundamental or emergent, and these particles might hold the key. Leading voices in the field see this as more than equations on a chalkboard. Dr. Sarah Walker, a theoretical physicist working on quantum origins, puts it starkly. We're not just studying particles, we're asking whether reality has layers we've never perceived, dimensions, forces, or even sentient structures beyond our comprehension. Meanwhile, cosmologist Dr. Neil Turok argues the opposite. The obsession with hidden particles might blind us to simpler truths. Perhaps dark energy is a mirror, showing us where our math fails to capture nature's elegance. The most thrilling possibility, that these particles bridge science and metaphysics. If they reveal connections between quantum fluctuations and cosmic expansion, we might finally understand how the infinitesimal shapes the infinite. Or they could unveil a cosmos far weirder than we've dared to imagine, where universes bubble up from quantum foam, each with its own physics, and dark energy is just one thread in a tapestry beyond space-time. One thing's certain, the answers won't just fill textbooks. They'll force us to rethink what it means to exist in a universe where the rules are still being written. And whether those 38 particles are real or red herrings, the search itself proves something profound, that humanity's curiosity stretches as far as the cosmos we're trying to decode. Lisa Randall, the trailblazing physicist known for her work on extra dimensions, puts it bluntly. In physics, we don't get to choose which ideas turn out to be true, nature decides. When asked about the 38-particle theory, she acknowledges the skepticism but points to history. Every major breakthrough started as speculation. The Higgs boson was just math on a page for decades before we found it. Her colleague Sean Carroll echoes this with a twist. The real question isn't whether these particles exist, it's whether we're asking the right questions to find them. Dark energy might not play by the rules we're used to, This tension between bold theorizing and rigorous proof isn't new. Think back to the early 20th century when quantum mechanics upended classical physics. Pioneers like Bohr and Einstein clashed over ideas that seemed absurd: particles behaving as waves, cats simultaneously alive and dead. Today's debate over dark energy particles mirrors that revolutionary era. Some researchers argue we're overdue for another paradigm shift, while others warn against chasing phantoms. Nobel laureate Adam Rees, who co-discovered cosmic acceleration, strikes a middle ground. What looks like wild speculation today could be textbook material tomorrow. But we've got to test, no shortcuts. The parallels run deeper. Just as the Michelson-Morley experiments failed attempt to detect the ether unexpectedly paved the way for relativity, today's null results in particle searches are quietly reshaping theories. When the Large Hadron Collider didn't find supersymmetry where many predicted, it didn't kill the idea, it forced refinements. Theoretical physicist Nima Arkani Hamed frames this beautifully. Science isn't about being right. It's about being less wrong over time. That iterative process where even dead ends illuminate the path is playing out now in labs from CERN to the South Pole, where detectors scan for dark energy's fingerprints in the ice. What makes this moment unique is the sheer breadth of approaches. Unlike past revolutions that hinged on single experiments, today's hunt spans colliders, telescopes, quantum sensors, and even AI-driven simulations. It's as if we're assembling a cosmic jigsaw puzzle where the pieces keep changing shape. As Randall observes, the universe has a way of surprising us just when we think we've got it figured out. Whether those surprises include 38 new particles or something even stranger, one thing's certain: the answers won't just resolve a mystery. They'll reveal how much we still have left to discover. History has a way of rewarding those who dare to predict the unseen. In the mid-19th century, astronomers noticed Uranus wobbling in its orbit as if tugged by an invisible hand. Instead of dismissing it as a glitch, mathematicians calculated the position of an unseen planet, Neptune, before telescopes ever spotted it. A century later, physicists predicted the Higgs boson's existence decades before the Large Hadron Collider confirmed it. These weren't lucky guesses, they were triumphs of mathematics guiding us to truths hidden in plain sight. Now, as we hunt for those 38 elusive particles tied to dark energy, we're walking the same path where equations on a chalkboard could outpace even our most advanced detectors. Mathematics has always been the silent partner in discovery, whispering clues where our senses fail. Einstein's field equations predicted gravitational waves a century before LIGO detected them. Paul Dirac's math conjured antimatter before a single positron was observed. Today, the numbers are hinting at something equally profound: that dark energy's secrets might be encoded in the geometry of extra dimensions or the symmetry-breaking patterns of quantum fields. Theories like supersymmetry and string theory didn't emerge from lab experiments, they sprang from mathematicians spotting elegant patterns that demanded new particles to balance the cosmic ledger. Yet this isn't just about solving equations. The challenge lies in bridging abstract math with tangible reality. Take axions, initially dreamed up to fix a quantum calculation. They're now leading candidates for both dark matter and dark energy. Or consider Kaluza-Klein theory, which unites gravity and electromagnetism by adding a hidden fifth dimension. An idea that seemed pure fantasy until researchers realized such dimensions could compactify into particles we've yet to detect. The irony: some of these particles might be too massive for our colliders or too weakly interacting for our labs, leaving math as our only compass in the search. Critics argue this reliance on theory risks drifting into speculation, but history's rebuttal is clear. every era's unprovable ideas became the next generation's textbooks. The neutrino was once dismissed as an impossible ghost until it was caught. Black holes were mathematical curiosities until telescopes proved them real. The difference now is scale. Dark energy's particles might not just fill gaps in our knowledge. They could rewrite the rules of what's possible, revealing forces that operate across hidden dimensions or fluctuate with the expansion of space itself. The beauty of this moment is the convergence of tools at our disposal. Supercomputers simulate universes with different dark energy parameters, testing which math holds up. Machine learning sifts through noise in particle collisions, hunting anomalies no human could spot. And next-generation telescopes map the cosmos in unprecedented detail, turning the universe into a lab where theories live or die by observation. Mathematics lights the way, but it's experiments that confirm whether we've decoded reality or need to go back to the chalkboard. So could dark energy be our next Neptune moment? Perhaps, but it might also be something grander, not just the discovery of a particle, but the unveiling of a hidden layer of physics where math and nature dance in ways we're only beginning to imagine. The equations are talking. All we have to do is listen. Mathematics doesn't just describe the universe, it often writes the first draft of reality. String theory's elegant equations, for instance, didn't emerge from a microscope or telescope. They sprang from mathematicians tracing the contours of extra dimensions on chalkboards. Those 38 hypothetical particles tied to dark energy, they're no different. Advanced topology, the study of shapes stretching beyond our three-dimensional intuition, suggests these particles could be knots in space-time's fabric. Group theory, which explores symmetries in abstract systems, hints at how they might interact. The math isn't just guessing, it's constructing a blueprint for forces we've yet to witness. But here's the twist. If these particles exist, they might not be hiding in the places we've searched before. Forget massive colliders for a moment. Imagine ancient gold mines, their depths shielded from cosmic noise, housing detectors so sensitive they could catch the faintest shiver of a passing action. Or consider the icy silence of Antarctica, where observatories like IceCube monitor neutrinos and might stumble upon sterile cousins whispering secrets about dark energy. Even the human body, bombarded by billions of particles every second, could inadvertently become a detector if only we knew how to read the signals. Then there's the cosmos itself, the ultimate laboratory. Neutron stars, those dense remnants of supernova, might spin with slight irregularities if certain dark energy particles tug at their cores. The cosmic microwave background, that faint glow from the universe's infancy, could bear faint imprints like fingerprints on glass from particles that slipped through the infant cosmos. Even black holes, those gravitational monsters, might reveal clues. As they evaporate over eons, they could emit particles tied to dark energy. Their death throws encoding answers in radiation we're just learning to decode. The most tantalizing hiding spots, though, might lie beyond our perception entirely. If some of these particles operate in extra dimensions, as string theory suggests, they could be everywhere and nowhere, passing through walls, planets, even us, like ghosts walking through walls. Detecting them wouldn't require brute force but ingenuity, manipulating magnetic fields in just the right way, or tuning quantum sensors to frequencies we've never considered. It's like trying to hear a symphony played in a key beyond human hearing. The notes are there, if only we build the right instrument. History shows us that breakthroughs often come from the unlikeliest places. The positron, antimatter's first hint, was found in cosmic rays, not a lab. The Higgs boson emerged from a machine built to probe energies once thought unreachable. Those 38 particles could follow the same script, hidden not in the noise, but in the quiet corners we've overlooked. The universe rarely reveals its secrets on demand. But with math as our map and creativity as our compass, we're closer than ever to turning speculation into discovery. Neutron stars, those ultra-dense remnants of supernova, might seem like unlikely dark energy detectors until you consider their precision. These cosmic lighthouses spin with near-perfect regularity, their rotations so stable they rival atomic clocks. But if certain dark energy particles interact with their crushing gravitational fields, they could cause barely perceptible wobbles in that spin. Teams are already monitoring pulsars rapidly spinning neutron stars that beam radio waves like cosmic metronomes for any minute deviations. A timing glitch as small as a millionth of a second could betray the presence of particles streaming through space, gently nudging these stellar corpses off rhythm. Then there's the symphony of colliding black holes. When these titans merge, they shake the fabric of space-time itself, sending gravitational waves rippling across the universe. Hidden in those ripples might be faint echoes of dark energy's influence, subtle distortions that reveal how these particles warp gravity over cosmic distances. The next generation of gravitational wave observatories, like the space-based LHC mission, will listen for these whispers with unprecedented sensitivity. Imagine detecting a vibration smaller than an atom's width across millions of miles, all to catch a particle that might not even obey the known laws of physics. But some of the most ingenious searches happen right here on Earth in labs where scientists exploit quantum entanglement's spooky connections. By entangling particles and measuring how their states change, researchers hope to spot interruptions caused by passing dark energy particles. It's like setting up a network of invisible tripwires. If something unseen brushes against one particle, its entangled partner will twitch in response, no matter how far apart they are. Even humble atomic clocks are joining the hunt. These ultra-precise timekeepers, accurate to within a second over billions of years, could detect dark energy's particles through minuscule changes in their tick rates. If certain particles alter fundamental constants like the fine structure constant, a number governing how light and matter interact, atomic clocks would feel it first. Experiments comparing clocks placed at different altitudes have already begun probing this possibility, turning time itself into a dark energy sensor. The timeline for discovery remains wide open. Some theories suggest we could stumble upon evidence within the next decade, especially if dark energy's particles leave faint traces in existing data. Others caution we may need entirely new technologies like quantum gravity sensors or space-based particle traps to crack the case. What's certain is that the search has entered uncharted territory, where the next breakthrough might come from a pulsar's hiccup, a lab's entangled particles, or an anomaly no one anticipated. The universe rarely reveals its secrets on demand, but with every unconventional method, we're learning to listen more closely to its quietest whispers. The timeline for unlocking dark energy's secrets stretches before us like a cosmic marathon, with no guarantee of when or where the finish line might appear. Next-generation experiments like the European Space Agency's Euclid Telescope, NASA and Nancy Grace Roman Space Telescope, and underground labs like the Deep Underground Neutrino Experiment are poised to revolutionize our search throughout the 2030s. But history whispers a crucial lesson. Breakthroughs rarely arrive on schedule. The Higgs boson took 50 years to confirm after its prediction. Gravitational waves were theorized a century before detection. Dark energy's particles could follow a similar arc or defy all expectations with a sudden revelation tomorrow in some overlooked dataset. Science's greatest discoveries often arrive unannounced, hiding in the noise until someone looks at the data just right. What makes this era unique is the sheer diversity of approaches converging on the same mystery. While massive projects dominate headlines, smaller-scale experiments could stumble upon clues first. A tabletop quantum sensor in Chicago might catch an action's faint signature before a billion-dollar collider does. An AI algorithm sifting through old telescope data could spot a pattern humans missed for decades. The universe doesn't care about our funding cycles or career timelines. It reveals itself on its own schedule. Yet even as we wait for answers, the societal ripple effects of this quest are already unfolding. Consider how past physics breakthroughs transformed civilization. Quantum mechanics birthed transistors, lasers, and the digital age. Discovering dark energy's particles could unlock equally profound technologies. Perhaps new energy sources harnessing vacuum fluctuations or propulsion systems manipulating space-time itself. The economic impact would be staggering, but so too would the philosophical shifts. Confirming that 95% of the universe operates by rules we're only beginning to grasp would humble even the most confident minds. On a practical level, solving dark energy could redefine global priorities. Climate models might need recalibrating if these particles influence cosmic expansion rates differently over time. Space exploration could take on new urgency if we confirm the universe's fate hinges on forces we've yet to master. Even education would transform. Imagine textbooks where dark energy isn't a placeholder, but an understood force with equations as fundamental as gravity. But the deepest impact might be cultural. Humanity has always measured its significance against the cosmos, from ancient civilizations tracking stars to Copernicus displacing Earth from the universe's center. Unraveling dark energy would mark another pivotal moment in that story. Either we'll find ourselves in a finely tuned universe where our existence depends on delicate balances, or adrift in a multiverse where physical laws vary wildly. Both possibilities reshape what it means to be human in the grand scheme. The search for these 38 particles isn't just a scientific endeavor, it's a mirror reflecting our species' hunger to understand its place in the unknown. Whether answers come in 5 years or 50, the journey itself is reshaping how we see reality, and that transformation, perhaps, is the most profound discovery of all. The implications of unraveling dark energy's secrets stretch far beyond textbooks and telescopes. They could redefine civilization itself. Imagine a future where energy isn't extracted from fossil fuels or sunlight, but harnessed directly from the quantum vacuum, tapping into the same mysterious force accelerating the universe's expansion. The concept might sound like science fiction, but so did nuclear fission before the 20th century. If dark energy's particles interact with space-time in ways we can manipulate, the energy crisis could become a relic of history. Picture spacecraft propelled not by rockets, but by bending the fabric of space itself, riding waves of dark energy like surfers on a cosmic tide. These aren't just fantasies, they're potential applications of physics we're only beginning to grasp. Yet the societal shift wouldn't stop at technology. Understanding dark energy could alter our very perception of time. Einstein showed us that time is elastic, warped by gravity and motion. If dark energy's particles influence space-time's expansion, they might also hold keys to time's arrow, why it flows forward, and whether that flow could ever be altered. Philosophers and scientists have debated these questions for centuries, but dark energy could turn speculation into testable science. The cultural ripple effects would be profound, forcing us to reconsider everything from religious cosmologies to the ethics of long-term planetary stewardship. But before we get ahead of ourselves, let's dispel some persistent myths. One common misconception is that dark energy is simply empty space pushing galaxies apart. In reality, it's far stranger, a dynamic force whose strength seems tied to the universe's volume, growing as space expands. another myth paints dark energy as a cosmic villain destined to tear reality apart. While the Big Rip scenario is possible, it's just one of many potential fates. Dark energy might weaken over time or even fluctuate in ways we can't yet predict. Perhaps the most dangerous misconception is that solving dark energy is purely an academic exercise. History teaches us that fundamental discoveries often spark revolutions no one foresaw. Quantum mechanics gave us lasers and microchips. Relativity enabled GPS. Dark energy's secrets could unlock advancements we can't yet conceive, whether in energy, medicine, or computing. The journey to understand it isn't just about mapping the cosmos. It's about preparing humanity for a future where the boundaries of physics are redrawn and the impossible becomes mundane. One of the most persistent myths about dark energy is that it's simply anti-gravity, a force that repels matter in the same way gravity attracts it. The truth is far more nuanced. Gravity, as Einstein taught us, isn't just a force, it's the curvature of space-time itself. Dark energy, on the other hand, appears to be a property of space, a kind of latent pressure woven into the fabric of the cosmos that grows as the universe expands. Picture blowing up a balloon with dots on its surface. Gravity would pull those dots together, but dark energy is like the rubber itself stretching, carrying the dots apart without any direct push or pull between them. This distinction isn't just semantics. It's fundamental to understanding why galaxies drift apart faster over time, not slower. Equally misleading is the assumption that the 38 hypothetical particles tied to dark energy must be related to dark matter. While both are dark in the sense that they don't interact with light, their roles couldn't be more different. Dark matter acts like cosmic glue, its gravitational pull holding galaxies together, while dark energy drives them apart. Think of dark matter as the scaffolding of the universe, invisible but essential for structure, while dark energy is the unseen hand stretching the canvas those structures are painted on. Confusing the two is like mistaking the foundation of a house for the wind that eventually weathers it away. These misconceptions aren't harmless. When public discourse blurs these lines, it can divert attention from the urgent need for research funding or fuel skepticism about the value of fundamental science. Imagine if early astronomers had dismissed Neptune's discovery as just another star, or we'd have missed a pivotal chapter in understanding our solar system. Similarly, dismissing dark energy as anti-gravity or conflating it with dark matter risks stalling progress on questions that could redefine physics. This brings us to the ethical heart of the pursuit. Science isn't done in a vacuum. It's a collective human endeavor with real-world consequences. Allocating resources to hunt for these 38 particles means prioritizing curiosity-driven research over immediate technological payoffs. Yet history shows that the most abstract discoveries often yield the most transformative applications. Quantum mechanics seemed like a philosophical footnote until it gave us transistors and MRI machines. Dark energy's secrets could unlock equally profound advancements, perhaps new energy sources, breakthroughs in materials science, or even insights into the universe's ultimate fate. But the ethics go deeper. If these particles reveal that dark energy's strength isn't constant, humanity might face a countdown to cosmic upheaval, a timeline for when the universe becomes inhospitable to life. Conversely, confirming its stability could offer a semblance of cosmic security. The knowledge alone carries weight. Do we have a responsibility to act on such discoveries, even if the timescales dwarf human history? And who gets to decide how that knowledge is used? The search for these particles isn't just about satisfying scientific curiosity. It's a testament to humanity's drive to understand its place in the cosmos. to confront uncomfortable truths and to prepare for futures we can't yet imagine. In a world often divided by short-term conflicts, this pursuit unites us under a shared sky full of questions, one where the next great discovery could rewrite not just textbooks, but our very sense of what it means to exist. Funding the search for dark energy's hidden particles forces us to confront one of society's most enduring dilemmas. How much should we invest in understanding the universe when pressing problems like poverty, disease, and climate change demand immediate solutions? The numbers are staggering. Projects like the James Webb Space Telescope cost $10 billion, while underground particle detectors require decades of sustained investment with no guaranteed payoff. Critics argue these funds could vaccinate millions or develop clean energy technologies, but history reveals a counterintuitive truth. Abstract research often yields the most transformative practical breakthroughs. The discovery of quantum mechanics, once considered pure intellectual curiosity, gave us everything from smartphones to cancer treatments. Similarly, unraveling dark energy could unlock revolutionary energy sources or propulsion systems that solve problems we can't yet anticipate. This tension between present needs and future possibilities plays out in funding debates worldwide. Governments must weigh short-term political cycles against science's long timelines, where today's experiments might bear fruit only for future generations. The ethical calculus becomes even more complex when considering who benefits. Space exploration has historically favored wealthy nations, while developing countries face more urgent challenges. Yet international collaborations like the Square Kilometre Array Telescope in South Africa demonstrate how cutting-edge research can drive local education, infrastructure, and high-tech job creation, proof that abstract science and societal progress aren't mutually exclusive. What often gets overlooked is how amateur scientists and citizen researchers are rewriting the rules of participation. You don't need a billion-dollar lab to contribute to cosmology. Projects like Einstein at Home harness spare computing power from volunteers' laptops to analyze gravitational wave data, while platforms like Zooniverse let anyone classify galaxies from their smartphones. High school teachers have helped discover pulsars, and backyard astronomers routinely spot supernova. The search for dark energy's particles could follow suit. Imagine distributed networks of low-cost quantum sensors in schools worldwide, or crowd-funded experiments testing unconventional theories rejected by mainstream funding bodies. The most exciting developments often emerge from these fringe efforts. Consider how the Arduino microcontroller, originally designed for students, now powers prototype particle detectors. Or how open-source AI tools allow independent researchers to sift through astronomical data for anomalies. When the Large Hadron Collider confirmed the Higgs boson's existence, it validated decades of theoretical work. But the next breakthrough might come from a garage lab running an ingenious low-budget experiment. This democratization of cosmic exploration changes the ethics equation dramatically. If cutting-edge research no longer requires exclusive access to elite institutions, the debate shifts from "should we fund this?" to "how can we empower more minds to contribute?" The answer might lie in hybrid models where governments fund foundational infrastructure while communities and citizen scientists build on it creatively. After all, dark energy doesn't discriminate. Its secrets are waiting for anyone clever enough to ask the right questions, regardless of their credentials or budget. You don't need a PhD or a billion-dollar lab to join the hunt for dark energy's secrets. Some of the most exciting breakthroughs in modern astronomy have come from everyday people, teachers, students, even hobbyists analyzing data that's freely available online. Projects like Einstein at Home harness the idle processing power of thousands of personal computers worldwide. crunching through gravitational wave signals or pulsar timings in search of anomalies that might hint at dark energy's influence. It's like having a cosmic detective squad where anyone with an internet connection can help piece together the puzzle. Take the case of Galaxy Zoo, a crowdsourcing initiative that enlisted volunteers to classify millions of galaxies from telescope images. What began as a way to tackle data overload led to genuine discoveries, including a never-before-seen type of galaxy dubbed green peas. Now imagine applying that same collective brainpower to dark energy's mysteries. Platforms like Zooniverse and NAS, a citizen science portal, let you sift through real astronomical data, searching for subtle patterns in galaxy distributions or quirks in supernova light curves, clues that professional researchers might overlook. The beauty of citizen science isn't just in its democratic spirit, it's in the sheer diversity of perspectives it brings. A retired engineer might spot a statistical oddity in quasar data that a career astrophysicist would dismiss as noise. A high school student could stumble upon an unusual correlation in cosmic microwave background maps while working on a science fair project. History shows that transformative ideas often come from outsiders unconstrained by conventional thinking. When it comes to decoding dark energy, the next big lead might not emerge from a prestigious university lab, but from someone's living room. But the unanswered questions loom large. Why does dark energy's strength appear so finely tuned, balancing on a knife's edge between tearing the universe apart and letting it collapse? If those 38 hypothetical particles exist, why haven't they shown up in our detectors yet? Could they be hiding in plain sight, masquerading as statistical flukes or measurement errors in existing data? The deeper we dig, the more we realize how much we don't know, and that's where the real adventure begins. Some theorists argue we're missing a fundamental symmetry in nature, a mathematical elegance that would neatly explain dark energy's behavior. Others suspect our very framework for measuring cosmic expansion might be flawed, like trying to gauge the speed of a car with a broken odometer. And then there's the radical possibility that dark energy isn't a single phenomenon at all, but the net effect of multiple undiscovered forces interacting in ways we can't yet imagine. What makes this moment so electrifying is that the tools to solve these riddles are within reach, not just for elite researchers, but for anyone curious enough to join the search. Whether you're contributing CPU cycles to a distributed computing project or classifying galaxies on your lunch break, you're part of a grand collaborative effort to map the invisible architecture of reality. The universe's greatest mysteries won't surrender their secrets easily, but with enough eyes on the data, enough minds turning over the possibilities, the next breakthrough could come from anywhere. Even if all 38 of these hypothetical particles are real, their discovery would only mark the beginning of a far deeper mystery. How do they interact? Do they communicate through forces we've never witnessed? Or are they solitary wanderers, indifferent to everything except the fabric of space itself? Some might be stable, lingering unchanged since the Big Bang, while others could be ephemeral, flickering in and out of existence within fractions of a second. Picture a cosmic symphony where some instruments play a single note and vanish, while others hum continuously beneath the surface of reality. Then there's the question of structure. Do these particles float freely, or could they clump together, forming invisible frameworks that shape the universe in ways we can't yet perceive? Imagine if dark energy isn't just a uniform mist but a dynamic network, with dense nodes and faint filaments stretching across the cosmos like an unseen skeleton. If that's true, then the empty voids between galaxies might not be so empty after all. They could be threaded with dark energy's hidden architecture, subtly guiding the universe's expansion. But here's the twist. Every answer science uncovers tends to reveal even more questions. Confirming these particles' existence would force us to ask why they have the properties they do, whether their masses, spins, or charges are arbitrary or dictated by some deeper symmetry. It's like peeling an onion with infinite layers. Each discovery pulls back another veil, exposing new puzzles beneath. That's the nature of exploration, whether we're charting uncharted oceans or probing the quantum void. Of course, there's always the possibility that the particle hunt comes up empty, that after decades of searching, we find no trace of these 38 theoretical entities. If that happens, the game changes entirely. Some scientists argue we might need to overhaul our understanding of gravity itself, tweaking Einstein's equations to account for cosmic acceleration without inventing new particles. Others propose even wilder ideas that dark energy isn't a force at all, but an illusion caused by our three-dimensional perspective on a higher dimensional universe. The beauty of this moment is that we're not locked into a single path. Physics thrives when ideas collide, when competing theories are tested against the harsh light of evidence. Whether the answers lie in particles, revised gravity, or something beyond our current imagination, one thing's certain: the universe is far stranger than we've dared to assume. And that's what makes the hunt so exhilarating, not just the prospect of finding answers, but the guarantee that whatever we discover will defy our expectations in ways we can't yet fathom. What if, after decades of searching, those 38 elusive particles never materialize? Science has a long history of dead ends and course corrections. Sometimes the most profound breakthroughs come from realizing we've been asking the wrong questions. Enter the bold thinkers proposing radical alternatives, theories so outside the mainstream they'd rewrite physics from the ground up. Take emergent gravity, the idea that gravity isn't a fundamental force at all, but a side effect of deeper quantum processes, like how temperature emerges from countless random molecular motions. Dutch physicist Eric Verland's controversial theory suggests dark energy's effects could just be gravity's hidden rules revealing themselves at cosmic scales, no exotic particles required. Then there's the holographic principle, which posits our three-dimensional universe might be a projection from a two-dimensional surface at its boundaries, an idea borrowed from black hole physics where information gets encoded on event horizons. If true, dark energy could be an artifact of this cosmic encoding, a shadow cast by deeper mathematical structures we're only beginning to grasp. These aren't fringe ideas, they're serious attempts to explain observations that stubbornly resist conventional explanations. After all, quantum mechanics and relativity once seemed equally outlandish before revolutionizing our understanding of reality. Skeptics of the 38-particle approach raise compelling objections. Nobel laureate David Gross compares particle physics to filling a taxicab with theorists. Eventually, you have to stop adding passengers. His concern: inventing new particles for every unexplained phenomenon risks creating a zoo of hypothetical entities without unifying principles. Others point to history. When Mercury's orbit defied Newton's predictions, scientists initially proposed a hidden planet called Vulcan rather than questioning gravity itself. Einstein's relativity provided the real answer, a cautionary tale about clinging to familiar frameworks when nature demands radical rethinking. Yet dismissing the particle hunt entirely would be premature. As physicist Nima Arkani-Hamed reminds us, the universe is under no obligation to make sense to you. Those 38 particles might still be waiting in unexplored energy ranges or hidden behind detection thresholds. The true path forward likely involves both approaches, pushing particle searches to their limits while nurturing alternative theories that could survive even if the searches come up empty. This duality isn't weakness, it's science's greatest strength. Every null result narrows the possibilities. Every failed experiment teaches us something new about where not to look. The most exciting possibility, that both camps are partly right, that dark energy emerges from some unimaginable synthesis of particles and space-time geometry we've yet to conceive. Just as light revealed itself to be both particle and wave, dark energy might demand multiple perspectives to fully unravel. What matters isn't being proven right, but asking questions bold enough to survive being proven wrong. After all, the universe hasn't changed to fit our theories. We change our theories to fit the universe. And that process, messy and unpredictable as it is, remains humanity's most reliable compass in the unknown. Not everyone is convinced that piling on new particles is the right path forward. To some physicists, proposing 38 hypothetical entities to explain dark energy feels like adding epicycles. Those convoluted circles ancient astronomers used to patch up Earth-centered models of the solar system. The skeptics have a point. Science thrives on simplicity. Einstein's equation E equals mc squared packs universe-altering truth into 5 characters, while the standard model's elegance lies in how 17 particles orchestrate all known matter and forces. Introducing dozens more, it risks turning physics into a cosmic junk drawer where we keep tossing in new pieces whenever observations don't fit. But here's where the debate gets interesting. Elegance doesn't always mean simplicity. Think of a grand piano. Its polished exterior hides a labyrinth of strings, hammers, and pedals, each essential for creating music. The universe might operate the same way. What seems like unnecessary complexity could be the very mechanism that makes reality sing. When quarks were first proposed, critics dismissed them as mathematical contrivances. Now we know they're fundamental, their odd fractional charges and confinement making perfect sense within quantum chromodynamics' intricate rules. Those 38 particles might seem excessive today, but tomorrow they could be the missing notes in cosmology's symphony. The real tension lies in balancing Occam's razor, the principle that the simplest solution is often best with the universe's refusal to conform to our aesthetic preferences. Dark energy's behavior is undeniably weird. Its effects grow as space expands, defying intuition. Maybe that strangeness demands equally strange explanations. Or perhaps, as critics argue, we're overcomplicating things because we're missing a deeper insight, a single elegant tweak to gravity or quantum theory that renders those particles unnecessary. History favors both approaches. Kepler's elliptical orbits simplified Ptolemy's epicycles, while Dirac's equation introduced antimatter to preserve mathematical beauty. This isn't just academic nitpicking. How we frame the problem shapes where we look for answers. If you believe dark energy stems from undiscovered particles, you build bigger colliders and finer detectors. If you suspect it's a flaw in our gravity equations, you scrutinize galaxy rotations and cosmic expansion rates for discrepancies. Both paths have value. Theoretical diversity acts as a safeguard against groupthink. When rival ideas compete, science self-corrects. The luminiferous ether's demise paved the way for relativity. The Higgs-boson's discovery validated decades of particle theory. What makes this moment thrilling is that we're not locked into one narrative. The universe doesn't care whether we prefer elegance or complexity. It just is. Our job is to listen, test, and stay open to surprises. Whether the answer lies in 38 particles or a single stroke of genius, the journey itself is expanding the frontiers of human understanding. And that's what makes science alive. Science thrives when competing ideas collide. That's how breakthroughs emerge. While the 38-particle framework offers an elegant solution to dark energy's mysteries, clinging to a single hypothesis risks blind spots. History is littered with examples where unconventional thinking cracked cosmic puzzles. Take Fritz Zwicky, the astronomer who first proposed dark matter in the 1930s. His peers dismissed it as fantasy, yet decades later, his missing mass became foundational to cosmology. Similarly, the hunt for dark energy benefits from a vibrant ecosystem of theories, each challenging and refining the others. Funding this intellectual diversity isn't just academic, it's strategic. Governments and institutions face tough choices when allocating limited resources. Should they invest billions in particle colliders chasing hypothetical entities, or divert funds to radical revisions of gravity? The answer, increasingly, is both. Agencies like the National Science Foundation and the European Research Council now prioritize high-risk, high-reward grants, betting on maverick ideas that could upend paradigms. Private donors, too, are stepping in. Tech billionaires fund ventures like the Breakthrough Prize, awarding millions for audacious theories that traditional grant systems might overlook. This multi-pronged approach mirrors how Silicon Valley disrupts industries by backing competing innovations simultaneously. Imagine if physics had only pursued string theory while ignoring loop quantum gravity, or vice versa. Progress accelerates when ideas cross-pollinate. A particle physicist's calculation might inspire a cosmologist to rethink galaxy formation, while a rogue mathematician's equation could reveal hidden patterns in old collider data. Yet funding alone isn't enough. The real magic happens in collaborative spaces where theorists and experimentalists spar openly. Think of CERN seminars where Nobel laureates and grad students debate on equal footing, or online platforms like RZiv, where groundbreaking preprints circulate globally within hours. These environments nurture creativity while grounding wild ideas in empirical rigor. The lesson: dark energy's solution may not come from a lone genius or a single experiment, but from the friction between competing visions, each refining the other until truth emerges. Whether through particles, revised gravity, or something entirely unforeseen, the path to discovery is paved with diversity of thought. And that's where the next revolution begins. Unlocking dark energy's secrets isn't just a scientific challenge. It's a logistical and financial marathon demanding global coordination. NASA's and Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, carries a price tag of over $3 billion, while CERN's proposed Future Circular Collider could cost upwards of $20 billion. These projects don't just push technological boundaries, they stretch the limits of international budgets and political will, yet the stakes are too high to leave funding to chance. When governments hesitate, philanthropy steps in. Billionaires like Yuri Milner and the Simons Foundation have poured millions into dark energy research, funding everything from quantum sensors to AI-driven data analysis. But even these generous contributions are drops in the cosmic bucket compared to what's needed to build the next generation of detectors. The real innovation lies in how these resources are pooled across disciplines and borders. Take the Vera C. Rubin Observatory in Chile, a joint venture between the U.S. National Science Foundation and the Department of Energy, with contributions from dozens of international partners. Its legacy survey of space and time will map billions of galaxies, offering clues about dark energy's influence on cosmic structure. Meanwhile, underground labs like Italy's Gran Sasso National Laboratory leverage shared infrastructure to host multiple experiments, from neutrino detectors to action searches, maximizing every euro invested. This collaborative model proves that cracking dark energy isn't just about throwing money at problems, it's about strategic alliances that amplify each dollar's impact. Yet for every success story, there's a project teetering on the edge. the European Space Agency's Euclid telescope narrowly avoided cancellation twice due to budget disputes, while the U.S.-led dark energy spectroscopic instrument faced years of delays as funding waxed and waned. The harsh reality: breakthroughs don't happen on political timelines. A detector shelved today could have been the key to tomorrow's revelation, leaving gaps in data that might take decades to fill. The solution isn't just more money, it's smarter systems for sustaining long-term research. Endowments like the Heising-Simons Foundation's Dark Energy Initiative show promise, offering stable funding insulated from election cycles and economic downturns. What makes this moment pivotal is the unexpected partnerships emerging. Tech giants like Google and IBM are lending quantum computing power to simulate dark energy's effects, while universities crowdsource data analysis through platforms like Zooniverse. Even artists are joining the effort. The Dark Energy Survey collaborated with a composer to translate galactic data into music, revealing patterns that visual plots missed. These interdisciplinary connections aren't just decorative, they're expanding how we frame the problem. A biologist's insight into neural networks might refine how we map dark matter filaments, or a materials scientist's work on superconductors could revolutionize particle detectors. The takeaway: solving dark energy demands more than physicists in isolation. It requires a tapestry of expertise woven together by shared curiosity and resourced creatively. Whether through international treaties, private philanthropy, or grassroots innovation, the hunt for answers is reshaping how humanity tackles its grandest questions. And in that reshaping, we're discovering that the keys to the cosmos might lie as much in our ability to collaborate as in our capacity to calculate. The hunt for dark energy secrets isn't confined to any single discipline. It's a melting pot where cosmologists compare galaxy maps with particle physicists smashing atoms, while quantum computing experts simulate alternate realities and AI researchers sift through cosmic noise for hidden patterns. This cross-pollination is birthing ideas no field could have conceived alone. Take quantum computing. By modeling how hypothetical dark energy particles might interact at scales impossible for classical computers, we're glimpsing behaviors that defy intuition. Meanwhile, machine learning algorithms trained on decades of telescope data are spotting subtle correlations humans overlooked, like faint distortions in starlight that could trace back to dark energy's influence on space-time itself. But here's the twist: some of the most promising leads are emerging from pure serendipity. Consider how the cosmic microwave background was discovered. Two radio astronomers troubleshooting antenna static in 1965 stumbled upon the afterglow of the Big Bang. Similarly, the next breakthrough might come from a glitch in a quantum processor, an anomaly in an AI's galaxy classification, or even a student's side project repurposing medical imaging tech to map dark matter filaments. History shows that transformative discoveries often happen when someone asks, "Wait, why does this oddity keep showing up?" rather than rigidly following a predetermined path. The role of luck in science is both underrated and misunderstood. It's not about blind chance, it's about prepared minds recognizing significance in the unexpected. When the Laser Interferometer Gravitational Wave Observatory first detected ripples in space-time, the signal was so faint that earlier generations of detectors would have missed it entirely. But because researchers had spent years refining their tools and honing their expectations, they could spot the extraordinary in what might have seemed like noise. That's the dance between preparation and opportunity, building sensitive enough instruments to catch whispers from the universe, then staying open to the possibility that those whispers might say something entirely unanticipated. Nowhere is this more evident than in failed experiments. When particle colliders don't find the particles they were designed to detect, those null results aren't dead ends, they're signposts redirecting the search. The fact that supersymmetry hasn't appeared in expected energy ranges forced physicists to reconsider assumptions, leading to wilder ideas like split supersymmetry or hidden sector particles. Similarly, if dark energy's particles evade our current detectors, it might mean we're not just missing a puzzle piece, we might be holding the wrong puzzle altogether. The beauty of this interdisciplinary scramble is that the solution could come from anywhere. A materials scientist tweaking superconductors might inadvertently create a sensor sensitive to axions. A biologist's model of neural networks could inspire new ways to map dark energy's distribution. Even artists collaborating with astronomers, like those translating galactic surveys into sound, have spotted patterns that traditional analysis missed. When fields collide, preconceptions shatter, and that's where the real magic happens. After all, the universe doesn't care about academic boundaries. Its secrets await anyone clever enough to ask the right questions wherever they might be looking. Some of science's greatest discoveries arrived not through meticulous planning, but through pure, unscripted chance. Take penicillin, a mold spore drifting into Alexander Fleming's lab by accident, or the cosmic microwave background originally dismissed as pesky pigeon droppings on a radio antenna before revealing itself as the echo of the Big Bang. These weren't flukes, they were moments when prepared minds recognized the extraordinary hidden in the mundane. The search for dark energy's 38 particles could follow the same script. A glitch in a detector's readout, an anomaly in a graduate student's data plot, or even an unexpected signal buried in decades-old telescope archives might suddenly snap the puzzle into focus. Consider the story of the first gravitational wave detection. For years, LIGO sensors had picked up nothing but noise until one morning in 2015, when a chirp lasting less than a second sent shockwaves through physics. That signal, later traced to colliding black holes a billion light-years away, almost went unnoticed. It was so faint that earlier versions of the experiment would have missed it entirely. What changed? Not just better technology, but a culture of obsessive curiosity. Researchers had spent years training algorithms to distinguish cosmic whispers from terrestrial rumbles, and when the universe finally spoke, they were ready to listen. This mindset, part patience, part paranoia, fuels dark energy research today. Underground labs monitor particle collisions for statistical blips that defy expectations. Telescopes scan the sky for subtle distortions that might betray hidden forces. The key isn't just collecting data, but nurturing a willingness to question every assumption. When the Opera experiment in 2011 clocked neutrinos apparently breaking the speed of light, it turned out to be a loose cable, but that same vigilance applied differently could catch the first hints of an axion or sterile neutrino. Yet this openness comes at a cost. The psychological weight of chasing phantoms can grind even the most passionate scientists down. Imagine dedicating your career to hunting particles that might not exist, sifting through endless noise for a signal that may never come. The pressure to publish, the scramble for funding, the public skepticism, it's a marathon with no guaranteed finish line. Younger researchers, in particular, face a brutal choice: invest years in high-risk, high-reward pursuits, or play it safe with incremental projects that guarantee steady results. History offers cautionary tales. Pioneers like Vera Rubin, who helped prove dark matter's existence, faced decades of dismissal before their work was accepted. Others, like Nikola Tesla chasing wireless energy or Fred Hoyle defending his steady-state universe, veered into obsession as their theories crumbled. The line between visionary and outlier is often drawn in hindsight. Today's dark energy hunters walk that same tightrope, balancing conviction with adaptability, knowing their legacy hinges on nature's whims. The emotional toll extends beyond individuals. Whole collaborations can fracture under the strain of null results. When the Large Hadron Collider failed to find supersymmetry where many predicted, careers built on that elegant theory suddenly hung in the balance. Some pivoted, others doubled down, arguing the particles must lie just beyond current energy thresholds. These aren't just academic disputes, they're human dramas playing out in conference rooms and preprint servers, where reputations and life's work hinge on questions no one can yet answer. What keeps scientists going? Sometimes it's the sheer addictive thrill of the chase. There's a reason particle physicists joke that their field is like searching for a black cat in a dark room, except the cat might not exist and the room might not have walls. The uncertainty isn't a bug, it's the feature. Every failed experiment narrows the possibilities. Every unexpected result forces a rethink. That intellectual ferment, the sense of teetering on the edge of revelation, is what lures brilliant minds into the unknown despite the risks. And then there are the quiet victories, the grad student who spots a curious pattern in old data, the engineer who tweaks a detector just enough to hear the universe's faintest signals. For every headline-grabbing breakthrough, there are countless smaller moments where curiosity triumphs over frustration. The search for dark energy's particles isn't just about rewriting physics textbooks, it's a testament to human resilience, our stubborn refusal to accept that some doors must remain forever closed. The lesson here isn't just about science, it's about how we confront the unknown in any field. Whether you're an artist staring at a blank canvas or a programmer debugging impossible code, the same principles apply. Stay open to surprises, learn to sit with discomfort, and remember that the biggest leaps often start with a stumble. The universe doesn't reveal its secrets on demand, but it does reward those who keep showing up day after day, ready for the unexpected. Imagine spending your entire career chasing shadows, decades of designing experiments, scrutinizing data, and revising theories, all while wrestling with the possibility that the answers might lie just beyond your reach. This is the daily reality for scientists probing dark energy's mysteries, where progress is measured in millimeter advances and eureka moments are vanishingly rare. The psychological toll is profound. Theory fatigue sets in when elegant hypotheses crumble under data's harsh light, when years of work lead not to breakthroughs but to narrower constraints on what dark energy isn't. Younger researchers face existential dilemmas, invest prime years in high-risk pursuits that may never pan out, or pivot to safer projects with clearer payoffs. Even veterans confess to sleepless nights wondering if their life's work will end up a footnote in science's graveyard of beautiful but wrong ideas. Yet what keeps them going is the staggering scale of the potential payoff. Success wouldn't just mean adding particles to a textbook, it would redefine our understanding of reality's fabric. Picture the moment a detector finally registers an action's faint whisper, or a telescope pattern confirms that dark energy fluctuates over time. Laboratories would erupt in tears and cheers, not just for the discovery, but for the validation of decades spent laboring in uncertainty. Scientific reputations would be made overnight, yes, but more importantly, humanity would gain its first real foothold into the universe's hidden 95%. The ripple effects would transcend academia. A confirmed dark energy particle could unlock technologies as unimaginable as quantum computing seemed a century ago. Perhaps new energy sources harnessing vacuum fluctuations or propulsion systems bending space-time itself. Philosophically, it would force us to confront whether we inhabit a finely tuned universe or one of countless multiverses where physics varies wildly. Schools would teach dark energy's mechanics alongside gravity and electromagnetism, normalizing what's now esoteric, and for the researchers who endured the long uncertainty. Their perseverance would join the annals of science's greatest gambles, like the decade-long hunt for the Higgs boson or the century-spanning quest to detect gravitational waves. But here's the bittersweet truth: even success wouldn't spell closure. Every answered question births new ones. If we isolate one of those 38 particles, we'd immediately ask how it interacts with others, why it has specific properties, and whether deeper layers lurk beneath. Science's horizon always recedes, but that's the thrill. The researchers who have devoted their lives to this puzzle know the real reward isn't a tidy ending, but the chance to keep peeling back the universe's infinite mysteries, one stubborn layer at a time. Finding even one of those 38 elusive particles would send shockwaves through physics, but confirming dark energy's true nature would rewrite civilization's understanding of reality itself. Picture the moment a lab's alert chimes, a telescope's data spikes, or a supercomputer's simulation snaps into focus, revealing the hidden architect behind the universe's accelerating expansion. The implications would dwarf past scientific revolutions. Copernicus displaced Earth from the cosmos's center. Darwin connected life to ancient origins. Einstein revealed time's flexibility. Dark energy's unraveling could join this pantheon, answering a question that's haunted humanity for millennia. What is the universe made of, and how does it truly work? The ripples would extend far beyond academia. Consider how quantum mechanics birthed transistors, lasers, and the digital age. Dark energy's mastery might unlock technologies we can't yet fathom. Energy sources tapping into space's vacuum, propulsion systems warping space-time, or sensors detecting hidden dimensions. Industries from computing to construction could be transformed by materials engineered with dark energy's rules in mind. Even philosophy and theology would grapple with the implications. Does a universe governed by such precise, yet invisible forces suggest deeper design or merely deeper complexity? But the path to discovery isn't linear. Every great scientific leap began with fragments, a discrepancy in Mercury's orbit hinting at relativity, a faint glow in a radio antenna betraying the Big Bang's echo. Dark energy's revelation might unfold similarly. First a statistical anomaly, then a tentative signal, finally a consensus that reshapes textbooks. The process will be messy, contested, and utterly exhilarating. For now, the hunt continues in underground labs where scientists listen for particles quieter than whispers, in space telescopes mapping the cosmos's accelerating stretch, and in equations scribbled on whiteboards, each a potential key to the universe's greatest secret. Whether the answer lies in particles, revised gravity, or something beyond our imagination, one truth remains: we're closer than ever to lighting up the dark. The enigma of dark energy isn't just another scientific puzzle, it's a mirror reflecting humanity's relentless drive to comprehend the incomprehensible. Picture this: right now, beneath mountains in silent labs, inside sprawling particle colliders, and atop remote observatories, thousands of researchers are chasing ghosts. They're tuning instruments to hear whispers from the quantum void, building detectors sensitive enough to catch shadows, and running simulations of universes with different rules, all in pursuit of those 38 elusive particles that could rewrite physics. This isn't just academic curiosity, it's a collective leap into the unknown, fueled by the conviction that nature's deepest truths are worth decades of dead ends and fleeting glimpses. What makes this quest so extraordinary is how it transcends generations. Today's grad students analyzing data from the James Webb Space Telescope stand on the shoulders of pioneers like Vera Rubin, who first uncovered dark matter's fingerprints, and Saul Perlmutter, whose team shocked the world by proving cosmic acceleration. In another decade, new minds will build on today's work, perhaps using technologies we can't yet imagine: quantum gravity sensors in orbit, AI-powered telescopes scanning entire skies nightly, or colliders harnessing energies that make the LHC seem quaint. Progress isn't a straight line. It's a relay race where each handoff of knowledge and tools inches us closer to the finish. But here's the beautiful paradox. Even if we never find those 38 particles, the search itself reshapes our understanding. Every null result, every experiment that comes up empty, forces us to ask better questions. When the Michelson-Morley experiment failed to detect the luminiferous ether in 1887, it didn't mark the end of physics, it paved the way for Einstein's relativity. Similarly, today's so-called failures are quietly ruling out possibilities, narrowing the path to truth. The universe doesn't owe us easy answers, but it does reward persistence. So what's next? The horizon gleams with possibility. The Vera Rubin Observatory will soon map billions of galaxies in unprecedented detail, hunting for dark energy's fingerprints in cosmic structures. The LISA mission will listen for gravitational waves from colliding supermassive black holes, potentially revealing how dark energy warps space-time. Meanwhile, tabletop experiments are achieving sensitivities that would have seemed impossible a decade ago, probing for axions and other exotic particles with setups no larger than a desk. The breakthrough might come from a massive international project, or from a lone researcher spotting an anomaly in old data, the way Jocelyn Bell discovered pulsars by noticing scruff on her radio charts. As we peer into the abyss of the unknown, one truth becomes clear: dark energy isn't just something out there. It's woven into the fabric of reality, stretching space itself, shaping the fate of everything from galactic clusters to the atoms in your hands. Unraveling its secrets won't just tell us why the universe expands, it'll reveal whether we're living in a finely tuned cosmic masterpiece, a random bubble in a multiverse, or something stranger still. The journey is far from over, but every observation, every calculation, every late-night lab session brings us closer to illumination. Keep questioning, keep exploring, and above all, never stop wondering what else is hiding in the dark.